A1 session 1 is about Thread 1.3. We're very close to launching Thread 1.3. It's been in progress for a couple of years. There might be new people that haven't been involved from the beginning. And so I thought we would do a brief overview of how we got to Thread 1.3. And is there an agenda slide? Rusi, can you go to the next slide? Okay, so we're going to talk, like I said, give you a little bit of overview and the evolution of how we got to Thread 1.3. And then we're going to talk about the use cases. So how did these use cases get defined? Not how they got defined, but what were the use cases that drove 1.3 and how did that get translated into features that are in 1.3? And we have a couple of speakers, Sam and Stuart are going to give kind of tutorials about the 1.3 features. And then we'll have a demo. So let's move on. Like I said, since we've lost a little bit of time here, I'm not going to spend a lot of time on the thread overview because I think everybody here probably knows it all. But yes, next slide. Okay. Okay, so Thread. All right, so Thread has been in the market, like you saw from this morning's presentation, for a few years now. And over the last 18 months, we've seen a real growth in the adoption of Thread. And it drives a lot of different use cases with Thread for IoT, and some of the key capabilities and features that distinguish Thread versus other technologies for these use cases are the mesh network being a reliable, self-forming, self-healing network, also being based on IP and having that direct communication, and low power. So I think everybody here is familiar with these benefits, and Rohit also explained them well in his presentation. So we can move to the next slide. This is the stack diagram to show where Thread fits into the overall picture. And you see we have Matter up at the top, but really Thread is application layer agnostic. So any application layer, IP-based application layer can work with Thread, and Thread is the network transport. And moving on, like I said, I'm going through these quickly because I think everybody here is very familiar with Thread. When we launched Thread, these were the key messages, and they still stand today about the key capabilities: low power, resilient, IP-based, and open protocol, secure, while also user-friendly. This is a diagram that shows in a smart home environment, what does a topology look like with Thread, using Matter as an example. So a Thread network has end devices or battery operated devices. And then we also have mesh extenders. Now in technical terms, you guys are probably used to thinking of it as Thread routers. Marketing is renaming that to mesh extenders because it's confusing to the consumers and users. To a Thread router gets confused as like a Wi-Fi router. So we're saying mesh extenders. Those are the powered devices that really create the mesh network. And the more devices you put on there, it gets larger or wider coverage. And then the border router is the key capability that ties it and connects it to the other networks. So you'll see we have 2 new badges now that will launch with Thread 1.3 to identify that this device is a border router or that this device requires a border router. And I think it's really critical that we educate the market and consumers on that when they're buying, especially when they're buying Matter devices, because Matter will run with Wi-Fi or Thread or both. And consumers need to understand if they have a Thread with Matter device that they need some other device in their network that connects them to the internet. So this is the new topology diagram and also the new badges that we'll use to educate about the purpose of a border router or the dependency on a border router. Next slide. So even with all of that, as Thread was being deployed, 2 years ago, we started identifying some potential gaps to driving broader adoption of Thread. So we can skip this slide because I don't want to think people here understand the different devices. I'll just jump into the Thread 1.3 use cases. So we went through an effort within Thread Group to open up and say, what is it that we need to address in order to drive wider adoption and remove any other obstacles that might remain in deploying Thread? And so we used the marketing team along with the technical team to define market use cases. So we didn't define technical features. We defined what's the problem statement, why is that a problem, and what needs to be done to address it. So I'm going to skip these slides, Lucy, if you can just go to that slide that has the table. Yes. So in the end, we went through a process of vetting the different use cases through the marketing committee and technical committee, and had a vote on it in November of 2019 in Zug. And we streamlined to these 4 use cases. So standardizing IP connectivity to IP bearing non-thread networks. So this is basically border routers, and I'll talk about that on the next slide. Optimization and certified validation of TCP best practices in Thread, then Thread use case of service registry, and then lastly, the merging partitions over Wi-Fi and Ethernet. So what we're going to try to do is go into a little bit of detail about these with the tutorials, and I'm going to give you some initial background on the market use case for each of these. So if we go to the next slide. For the border router, we heard a lot over the years as Thread was being deployed that the lack of border routers was causing delays in deploying Thread, and that there wasn't a standard way to implement a border router, and that was a problem. And so this gives a lot more details on the technical side, but from a marketing perspective, we needed to standardize on what a Thread border router is and how to implement it. And so that was a key use case for what Thread 1.3, the code name was Duckhorn. Next slide. All right, so this another topic, the use case was service registry. So the problem statement was that devices on a Thread mesh network can't communicate to each other directly if they can't find each other. And so this affects all of our markets, and the way that this would be addressed is to have a service registry so that the devices can communicate and discover each other and communicate without cloud connectivity or an internet connection. All right. And then TCP for Thread. Stuart is going to go into a lot more detail on this, but it really revolved around, from the marketing use case, was around this capability to truly be all IP and be able to do bulk data transfers, such as doing over-the-air updates. And like I said, Stuart is going to go into much deeper detail on what the reason for this use case and how it gets used. And the next one is merging partitions. So Thread can form partitions, but due to lack of, may form partitions if there is not a 15.4 connectivity. So really the overall statement here was that we want to improve the user experience when Thread partitions are connected to Ethernet or Wi-Fi. So that's just, and like I said, there's detailed documents for each of those use cases that outline the market use case, what are the market forces, what are the target applications and capabilities, and the key aspects that need to be resolved. And then the technical committee took that and did the feasibility and turned it into Thread 1.3 spec. So now we're going to start with Sam, who's going to talk about, tell me again what he's talking about. Okay. Because I don't know between you and Sam who's talking what.
Okay. In the early days of Thread, the silicon vendors would produce SDKs that supported IP, because Thread is an IP technology, but it did not include TCP. And the same silicon vendors selling the same parts with the same processor and the same flash and the same RAM with Wi-Fi did include TCP, because naturally, why would you want a Wi-Fi device that can't do TCP IP? But I think because of the different background of Thread, there was a belief that for people with an automation background, you can stick some bytes in a packet and send it, and that's it. And when things are connected with a physical wire, you can do that. But when you have a multi-hop network like the Thread mesh, you need a mature transport protocol that has flow control and congestion control. And there was no technical barrier, because the same parts could run TCP on Wi-Fi. And we looked at this and we felt it was holding Thread back, because a developer considering making a product, they can buy a Wi-Fi part and they have the full TCP/IP protocol suite available. they made the same part with Thread, they're getting a more limited thing. So we looked into this and said, there's no reason for this limitation. Developers of applications should have the full menu of choices available so they can pick the best tool for the job. And we started looking into what was available. And we found some research done by a PhD student at Berkeley called Sam Kumar, where he had published research debunking many of the myths that you can't run TCP on a low-speed network, or you can't run TCP on a wireless network. And we invited Sam to come and talk to us, and we really liked the work that he was doing, and we asked him to contribute. And that's why Sam is presenting to us today. And I will hand over to Sam now and let him describe the path that led to where we are today. Thank you, Sam.
Thanks, Stuart, for the introduction. As he said, I'm a PhD student in computer science at UC Berkeley. And today I'll tell you about my open source work on adding TCP support in OpenThread. So the background is that as part of my PhD research, I studied TCP over low power wireless networks, particularly networks that, like Thread, are based on IEEE 802.15.4. Initially independent of my research, the Thread group in 2019 voted to require support for bulk transfer using TCP. And this requirement, as was just stated, is included in Thread 1.3. So as part of this effort, the Thread Technical Committee evaluated various solutions for running TCP, including my research. And the outcome of that was that they invited me to contribute my research work to OpenThread. And today I'll describe that open source work I did on adding TCP to OpenThread. So a central decision was which TCP implementations to use and what features to support. And the OpenThread developer community investigated various options for this. So this is a slide back from one of OpenThread's developer meetings. You don't have to read the whole slide, but the point here is that the community considered various TCP stacks. These are the columns over here. And they considered various TCP features. These are the rows over here. And as you can see from this, many of the candidates for an embedded TCP implementation targeted towards resource-constrained devices are highly simplified TCP implementations that don't support all of the TCP features. For example, micro IP and lightweight IP, which are two well-known resource-constrained embedded TCP implementations, don't support many of the features that you would see in a full-scale TCP stack in a regular operating system. Like, for example, FreeBSD supports all of them. Now, the OpenThread community chose to use TCP/LP, which is a TCP implementation geared toward low-power resource-constrained devices that supports all full-scale TCP features. So to say a little more about what TCP/LP is, it's the artifact of the research I did. So it is the full-scale TCP stack from FreeBSD, which I took and refactored in order to make it work well on resource-constrained IEEE 802.15.4 devices, typical of those you may see in a Thread network. And the TCP/LP is really the artifact. My research is focusing broadly on the question of how to make TCP work well over these networks. And we have a paper published that introduces the TCP/LP artifact. This was a broader investigation of this topic published at NSDI 2020. Once the OpenThread developer community decided to integrate TCP/LP into OpenThread, I've been doing open source work on taking my TCP/LP research code and turning it into production code and merging it and integrating it properly into the OpenThread code base. And I'm happy to announce that as of a couple of months ago, that work is now complete and ready for use. At this point, you can open up a TCP socket in OpenThread, send data over it, and it'll use TCP/LP to go ahead and send and receive data. An important concern early on in the process with the adoption of TCP, both in Thread, I believe, as well as OpenThread, was the question of what's the overhead of adding TCP. Because, even though the research I did shows, TCP works well, the question is, in practice, if you properly integrate TCP into the network stack and so on, what's the memory overhead going to be? So here's another slide from the OpenThread developer meetings where we look at the various choices. You can estimate what the overhead would be. For example, for TCP/LP, I took these numbers based on what we were able to achieve in the research. But now that the integration into OpenThread is complete, we can go back and revisit what the overhead really is. And the numbers turn out to be about a 20 kilobyte overhead in ROM size. So that's the amount of code it takes for TCP. And for RAM size, if you look at the connection state for the TCP protocol, for each connection you have open, it's 600 bytes of memory. Now, both of these numbers are actually pretty good, in my opinion. The 20 kilobytes, if you compare that to, for example, these sizes down here, which are the sizes of actually an application that uses OpenThread or just the core OpenThread libraries, it's about a 10% overhead. And that's probably a little less because these numbers have grown a little bit, these numbers over here, since the slide was made. And in terms of RAM size, 600 bytes is also pretty good because for a TCP connection, you would need several kilobytes of buffers anyway. So 600 bytes for connection state is pretty small in comparison to that. So overall, the takeaway here is that, looking at the final TCP implementation, it's actually not that heavyweight in terms of memory footprint. In the next part of the talk, I'm going to talk about what the API looks like for using TCP in OpenThread. So one of the key points I want you to take away from the API discussion is to understand how we modify the API from the traditional BSD sockets API you have on, say, Linux, in order to make TCP more suited for these resource-constrained devices you see in a thread network. So in our API, there are two main data types, OTTCP endpoint and OTTCP listener. Are you all still able to hear me? Yes, okay, I'm back, okay. I just saw the message in the chat. Okay, yeah, so there are two main data types. There's OTTCP endpoint and OTTCP listener. And the way to understand this is that OTTCP endpoint is representing one endpoint of an established connection. So you can use it to actually send data over TCP or receive data over TCP. And meanwhile, OTTCP listener is used to listen for incoming connections and accept them. And you accept them into endpoints, which you can then use to go ahead and transfer data. So in a typical BSD sockets-based API, these two functionalities would be combined into a single TCP socket. And part of a rationale in splitting them apart was to reduce memory usage, because it takes more memory for a TCP endpoint, which has to maintain the full TCP connection state compared to a TCP listener. And by splitting them apart, it makes it so that you only are paying the memory overhead for the part of TCP that you're using. Another change compared to the BSD sockets API is that we use callbacks to notify the application of TCP events. And this was partially done in order to make the TCP API work in the same vein as the rest of OpenThread. For example, your UDP API is also based on callbacks, and it's pretty common throughout that code. But it's also because, the perception in the space is that on these kinds of resource-constrained devices, threads are not always appropriate, and an event-driven architecture for concurrency is more efficient. And by making TCP work in that architecture, we're avoiding to add extra overhead and avoiding to change the programming model. And finally, I just want to say that throughout the TCP implementation on API, we designed it with memory constraints in mind. For example, the implementation does not use a general purpose memory allocator like malloc. And furthermore, the API given to the programmer allows the programmer to use the API without a general purpose memory allocator like malloc. So here are some examples to see how this looks in practice. So this first example here initializes the TCP endpoint. Now the point is that we have this variable STCP endpoint that the user that the programmer allocated, and then you call this initialize function on it. And but we have it as this variable. It could also be a field within another structure. It could be allocated on the heap with malloc if you want. It could be a global variable or a static variable. The point is that this API works where the user allocates this variable and then hands that memory over to the TCP stack, which is how we avoid the need for dynamic memory allocation. In contrast to APIs in contrast to other TCP APIs, like for example, the BSD sockets API or LWIP and so on. And for reference, the OpenThread UDP API works in exactly the same way, where you declare some OT UDP socket variable and then initialize it. So this isn't a new trick; it's just adapting what OpenThread already does to the context of TCP. Here's another example for sending out data on an established TCP connection. So here you declare this structure called a linked buffer, which contains a pointer M data to whatever you would like, and then M length sync how long that data string is. And then you do this ODTCP send by reference, which does not copy the data, but makes the linked buffer be part of the TCP send buffer. So what's the point here? Well, there are 2 points. The first one is that this M data field can point to anything that's addressable. So it can point to data you have in RAM, of course, but if you have some data in ROM that's just like you're sending some templated response to every client or something, and you're running a TCP server on this device, then you can also just point it directly to whatever data you have in ROM and save a bunch of memory that way. And the second point is that we aren't copying the data, and that reduces the memory usage further, because it means that you don't have to allocate another buffer into which to copy your data just for the sake of sending it out over TCP. Again, the overall takeaway here is that we departed in meaningful ways from the standard BSD API and instead chose an API appropriate for resource-constrained devices and in line with OpenThread's conventions. As I said, all this is in OpenThread, and in fact, you can see the official documentation on the OpenThread website at the first URL. Second, if you're interested in actually using TCP, I put together this demo, a video going through how to use a CLI tool in OpenThread to just start out by using TCP. So that may be useful as you get started with actually using this code. Finally, I want to say that I'm continuing to develop and maintain TCP in OpenThread, so feel free to reach out to me if you're interested. For example, if you're getting started with TCP, I can help you out. If you find any bugs, I can help to fix them. And finally, as always, I'm open to any feedback or suggestions on the TCP API or implementation. So feel free to reach out to me if you have any. And my contact information, in case you want to do that, is on this slide. So that's all I have prepared, and I'm happy to take any questions now.
I also want to congratulate Sam. I just want to congratulate Sam as well on this research paper he presented, was awarded this year the Applied Networking Research Prize, which is a prize of the IRTF, the Internet Research Task Force. You can find that at irtf.org/ANRP. So congratulations, Sam, for that as well. So it looks like we don't have any questions right now, but Sam has graciously offered, while continuing to do his PhD, to answer any questions people have. So if there are developers using the new code he's contributed to OpenThread, by all means, reach out to Sam and he can help if you have any questions about how to use it. And certainly if you find any bugs, he'll leap right on fixing those. Okay, is the microphone working? Okay, that's good. So we just covered how Sam added TCP to OpenThread, which brought Thread parts on par with their Wi-Fi equivalents. And there was another area where we identified that Thread needed parity with Wi-Fi. Today, it's very familiar to everybody. You can buy a Wi-Fi access point. It bridges your Wi-Fi onto your Ethernet, and Wi-Fi devices can act just like Ethernet devices. What we needed for Thread was the equivalent, but not done exactly the same, because just bridging the networks together is not very scalable. When Thread is a 1/4 megabit and your Ethernet might be gigabit, there's a big mismatch in speeds. So blindly flooding all the traffic in both directions was clearly not going to work. And this is where we took advantage of IPv6 routing. So for a Wi-Fi access point or a Thread border router, there are two key properties that we want. We need discovery so that clients can discover services that they want to talk to. And having done that discovery, we need connectivity in both directions. Those sound like fairly simple, obvious things, and in a way they are, but doing that in a way that is efficient and reliable is what we've been working on. This is my example network that I'll be using for talking about this. We have the blue network, which is Wi-Fi, which is a hub and spoke with the access point being the center. For most people, that access point is co-located with their internet gateway. For the purpose of this, that's not important because we're not talking outside the house. The orange network is the Thread network, which is not a star topology like Wi-Fi, it is a mesh. So let's start off with discovery. On Wi-Fi and Ethernet for the last 20 years or more, we have used multicast for discovery with many different multicast protocols, with Microsoft NetBIOS and AppleTalk and many, many things have all used multicast. And on fast wired Ethernet, that is reasonable. On a mesh network that's wireless, that is a lower speed, that becomes very wasteful. So we took the opportunity with Thread to design something better, and that is that the border router has a software entity, a piece of infrastructure called a service registry. And when a device on your Thread mesh, be it a light switch, a thermostat, a window sensor, whatever it is, when it is offering some service, instead of listening for multicasts and running its battery down, receiving all of those and answering them, it creates a registration with the service registry saying, this describes my identity, what port I'm listening on, what service I provide. If there are any queries, please answer those on my behalf. And that way I can save battery power and not have to waste battery and Wi-Fi wireless spectrum answering these queries. When you then take some existing device on Wi-Fi, which is expecting to use multicast for doing discovery, it sends out its multicast, which goes everywhere, and the devices that aren't interested ignore it. But in this case, the multicast goes to the service registry and sees that that's a query for something it knows about, and it sends back the answer. And now your device, in this example, a smartphone in your hand, has used multicast on Wi-Fi, but the thing it's discovered is not on the Wi-Fi, it is a couple of hops away on the Thread mesh. And that allows us to do fast, efficient, reliable discovery while keeping all that multicast traffic off the Thread mesh. We want discovery in the other direction as well. So devices on the Thread mesh can discover services on Wi-Fi, again, without polluting the Thread mesh with multicast traffic. So here, the node on the Thread mesh does a unicast query to the border router, which is running a software entity called a discovery proxy, and that handles multicast on behalf of the client. So when that query comes in, the discovery proxy will handle the multicast. It'll collect the answers and it sends those back to the thread client. So this gives us discovery in both directions, both services on the thread mesh looking, advertising to clients elsewhere, and clients on the thread mesh looking for services elsewhere, all done without burdening the thread mesh with multicast. So now we have multicast, and now we have service discovery working without using multicast. That is great. You can discover the IP address and port number for something you want to talk to. Of course, we need the communication to work. And this is where it was great to be able to take advantage of the smart design decision that the early designers of Thread made, which is to build this on IPv6. Because if we were using IPv4, we would be struggling a lot more. You have to use network address translation, and getting reliable bidirectional communication through NAT gateways is very difficult, or I would go so far as to say practically impossible to get fully reliable bidirectional NAT traversal. Thankfully, we don't have to do that because we have IPv6. And we built on existing capabilities in IPv6 to let us connect these networks together by using IPv6 routing instead of bridging at the Ethernet layer, which would involve flooding a lot of traffic. Every thread node already has a link local address and a mesh local address for communication within the mesh. We also want those nodes now to be able to communicate outside the mesh, so they need a third IPv6 address. And this is one of the great benefits of IPv6 stacks, is that they all support multiple addresses. So we have link local for one hop, we have mesh local within the mesh, and we want to configure a third one. Now, if your corporate network or your home ISP supports IPv6 DHCP prefix delegation, then you can actually get allocated a global IPv6 address that is reachable from anywhere within your enterprise, or in principle, if you want, from anywhere in the world. Now, you may have firewall rules and there may be security policies there, so you can choose how much access you want. But architecturally, IPv6 prefix delegation gives you the freedom to have, if you want, a globally routable address. If you don't have prefix delegation available, then the border router will automatically make up a random unique local address and configure that as the off-mesh communication prefix on the thread mesh. For most home users today, they will be using an automatically generated ULA. But for an enterprise that actually wants everything within a large building or a large campus of buildings to all be reachable, they can run prefix delegation and actually have all of these things be interconnected. In addition to configuring the thread nodes with the off-mesh communication prefix they should be using, the border router also uses IPv6 router advertisements to inform its neighbors on the Ethernet or Wi-Fi segment that if they want to reach an IP address within this prefix, then this router is the router to use to reach that. And that tells all of these blue nodes that if you have a packet addressed to prefix A, don't send it to your ISP, don't send it to default gateway, because it won't know what to do with it. Send it to the border router, because that is the router that has authority and offers reachability to that prefix. And when that router advertisement is sent out, devices on the Wi-Fi receive that and store that in their routing table. And now they know how to reach prefix A. If your network is configured for V6 already, then that's great. Your laptops, your smartphones, your tablets will have an address, an IPv6 address, either global or local, configured through router advertisements. And if that's the case, then that's great. the Thread 1.3 border routers also listen for those router advertisements. And if there are no V6 addresses configured on that link, then the border router will automatically step up and take on that responsibility. This will not be a globally reachable address without routing infrastructure, but it will create a randomly assigned ULA, unique local address, which is good enough for local communication between the Thread mesh and that adjacent infrastructure network. So in the event that you don't already have IPv6, the border router will do that for you. And now the device in your hand will configure a self-assigned address within that prefix. And now the device in your hand has an address of its own in prefix B, and it knows that to reach prefix A, its next hop router is the border router. And with those two things in place, we now have bidirectional connectivity. When your device sends out a packet addressed to some destination in prefix A, its routing table says send it to the border router, and once it gets there, the existing Thread mesh routing protocol knows the right path to get to the destination. And when the destination replies, the same kind of thing applies. A packet is generated going to destination in prefix B, and the Thread mesh doesn't know anything about that, but it knows it's outside the mesh. So the packet will make its way through the mesh to the border router, and the border router, by looking in its routing table, says, oh, this is an on-link prefix for my Wi-Fi network, so I will send it one hop to its final destination. So putting those two things together, we now have bidirectional discovery and bidirectional communication. Bit of background for people been involved in the technical committee and want to learn a bit of using existing building blocks and specifying how they should be used. So I don't need to read out all the words here. We have RFCs for discovery proxy. We also have drafts in their final stages for service registration and advertising proxy. For the bidirectional communication, these are RFCs from more than a decade ago, and those were mature, well understood, already implemented in current operating systems. So that was just a matter of making use of things that were already there. Our focus with Thread 1.3 is to meet the needs of Matter in time for Matter shipping. And I'm very happy to say that we already have multiple vendors fairly far along this path. Apple has the HomePod Mini and the Apple TV. Google has several Nest Hub products that have the 1.3 border router functionality. I know Eero is working on building it into the Eero access points, and Nanoleaf, which you wouldn't think of as being like Eero or like Nest Wi-Fi as being a home gateway access point kind of product. But because their products have a Thread radio and a Wi-Fi radio, they're ideal candidates to be a border router. And as a result of this, many customers are going to find that they have not just one, but multiple border router devices on their network. And that goes a long way to addressing this concern that you can buy a Wi-Fi device and just expect it to work, because most customers today have an access point already. You buy a Thread device, there is a question, well, do I need to buy a border router as well? And some people may still need to do that. But if you have one of these products, then in addition to whatever else it does for you, it is just incidentally a border router as well. And that saves you having to buy an extra piece of hardware. So that is the end of my presentation. We can take some questions.
So are there any border router things hitting kind of the industrial side of the market as well? Obviously, the Matter for now, that's huge for the consumer, but is there anything kind of more industrial?
The question is about border routers targeting industrial markets. All the products here are clearly consumer products. We would love to work with the vendors who address those markets. Speaking for myself as an Apple employee, that's not the market that we're in, but we would love to work with the companies that are. This software is going into OpenThread, so the same software we're writing is easily reusable in those other product categories.
Yeah.
Should we give you the mic?
Currently, Siemens is doing a commercial border router. We are on our way, and it should be available at least end of this year. So we decided to do that on our own, but we are also discussing with others to make, let's say, building network infrastructures also become thread infrastructures. Yeah, good. Thank you.
All right. So thank you again to Stuart and Sam, and talking about giving a Thread 1.3 overview. I think that's a lot of good information, but I think it's always fun to see it working in action on a real product. So I think Gabe graciously offered to show some of this working on his Eero devices.
Should I come up or can I just go from here?
You can join from Zoom. Is that okay to share from your? There you go, I guess. Are you on the Zoom, Gabe? Okay.
I wanted to share my screen though. Do you have a microphone? I just have to update my privacy settings to share my screen, Zoom, quit the meeting, rejoin the meeting. Can everyone see my screen? Sorry, it was a joke. I can see my own screen. Cool. Hi, everybody. Gabe Castle. I'm a product manager at Amazon. I work on the Eero team. I'm going to try to show you a few demos. Live demos are challenging. So first, we have a not live demo that Nathan and I
half an hour ago.
Yeah, Nathan and I created a little while ago. And this shows some work that Nanoleaf and Eero did together to sync or share credentials between our products. Let me try to get a bunch of stuff out of the screen so that you guys can actually see what's going on. Because I don't think I can make it any bigger. But basically what's happening here is Nathan is linking his Nanoleaf account with his Eero account. And so the Nanoleaf app using MDNS discovers that there is an Eero border router, and basically through an OAuth connection is able to get the thread credentials, and then Nanoleaf can join the Eero thread network. There are some other opportunities in the industry now to share credentials between companies, but this was something that we built last year. I think we've shown it before. Oops. I think you only captured like the login screen. But I think, I think we can imagine what might happen. So while Nathan's getting that up, a few other demos that I wanted to do today that I'll try to enlarge to hopefully make them useful. So over here, I have 2 Eros that are in a Wi-Fi mesh with each other. And of course, they're also in a thread mesh. So if we look at our router table, if this will work, yep. We have 2 Eros, and we also have 2 Nordic devices that are acting as routers. This is off my screen, potentially, maybe. So I think things that I wanted to show, Stuart talked about SRP proxy and SRP. Sam obviously talked a lot about TCP. And then I think one thing that we have integrated that might be cool to show is DNS64 and NAT64. So just flipping back and forth, let's download this video from Nathan and give that a go, just to kind of go a little bit in order. No. There's a small bug where we go into reader mode, so you can just ignore that. So we've linked our accounts, then we go back to the Nanoleaf app, and now Nanoleaf has received the thread credentials from Eero and actually can go and turn on the thread network if it happens to be off, and start joining devices to our network. So that's the experience that's in production there today. I'm going to pull up my cheat sheet notes because not as fast as other people. Let's see, what order should we go in? Let's look at SRP first. So I think Stuart did a much better job than I'll ever be able to around why SRP is important. Oops. So this is a Nordic reference board, which I think it will tell you. Yep. So 52840. So let's name it. Let's get its IP addresses. I think Jonathan Apton, anyone tell me if I'm doing things wrong, but I think we register its address for its host name, maybe. Let's try, maybe not. Let's see if we can just register the service and what happens. Did it show up? Oh, and am I on the right network? This is the other problem with a live demo when you have two thread networks in the same room. That's fair, yeah. But now I've switched over. Yeah, let's switch back and show yours. So kind of showing the same premise. Nathan attached some Nanoleaf bulbs, and sorry that, and my screen's still not updating. So let's see if I get back on. Cool. Is it updating? Thank you. It helps to have the people that wrote the CLI in the room. It's usually nice. Let's see. All right, so it's back. Sorry, I can't make this any bigger. So you all can come over later and see it if you want. But there are two Nanoleaf bulbs next to me that we've attached to this thread network, and they have registered with the HomeKit accessory protocol service. And so this is using the SRP proxy through an Eero border router in production. And
so the interesting thing here is Gabe's highlighted the HAP UDP services. This is the HomeKit accessory protocol, but Thread is protocol agnostic. So if you actually highlight the LTPDU UDP services, it's at the bottom of the, so these are mirrored services under our LTPDU protocol. It's a custom protocol that Nanoleaf runs. And so SRP is ready to do this, right? So these devices have been in production with Thread 1.3. The SRP server can host a number of different services on there. So HomeKit today, Matter tomorrow, proprietary, all of the above.
Cool. So I think I survived SRP. Let's go to TCP. And Sam has a really great YouTube video that I think is linked from OpenThread that describes exactly what I'm going to show here. But we do an init and we do a listen on a port. And this is on one of the two Nordic boards that I have right here. Then I'm going to go over to the other board. And I'm going to do, let's make this one bigger. I'm going to do an init here. And I'm going to connect to the link local of the partner. If I can get the little thing to go away. It's fun. And so we've made a TCP connection. We can send a hello, but it doesn't seem as fun as the benchmark command that Sam added. So this is basically streaming TCP back and forth as far as I understand. And we can see it over here. And then when it completes, it will actually print the TCP throughput between the connection. Stuart, anything you want to add on that demo? Great. Works beautifully. Cool. Trell, I'll get to in a little bit, very hard to demo. Let's look at DNS64 and NAT64. So if you imagine that you have a device that you want to be able to connect back to your cloud service or get something off of the public internet, and you're in a home that doesn't have native IPv6 from the ISP, DNS64, NAT64 is the way that you would do that. So let's go to one of our Nordic boards. I'll just copy and paste. But essentially, when the device registers with the SRP server, part of that process is that it figures out or it receives who might be a DNS resolver. And so in this case, there's an Eero that has put itself in the network data as providing DNS services. And if we look, we actually see that there are two Eeros that have registered our NAT64 prefix. So I can go and resolve the IPv4 version of Google, and we get a response. And then we can ping. Let's see, what's a good, what we like. Cool. So I'm pinging IPv4 Google from my Thread device. It actually worked. Pretty amazing. The last one's Trell. The fun demo of Trell is a little bit hard to set up, where I would have two Eeros, and we could basically iPerf across the encapsulated Thread mesh between the two devices that's running over Thread or Ethernet. Kind of the simple demo for the group, just to sort of prove to everyone that it's running, is to just show the Trell peers list. So basically, there is another Eero that this Eero has established a thread encapsulated connection with. In the case of Eero, that's over every Wi-Fi and Ethernet connection that might exist between those two devices. And so we have a much higher throughput kind of path that the mesh can take between the two devices. There's a component of Trell that uses service discovery, and so you can see the Trell service. I'm actually connected to a different Wi-Fi network that only has one Eero, which is why you only see one. But yeah, it works. I don't know. Jonathan, Stuart, anything else you guys want to see?
I was just
what?
going to say thank you, Gabe.
Sure.
That's very brave doing all those demos live.
Yeah. So I think the last thing that I'd add, and I think the most impressive thing to me, which is really standing on the shoulders of all of the work that Google and Apple have done. Everything that I just showed you is in production. This is production software. You can go buy an Eero, turn on Thread. All of this is in the product. So that I think that's really the message for the group is this is not a raw demo. This is like shipping software.
Congratulations. Thank you,
Thanks.
Gabe.
All right. Yes, thank you, Gabe. Thank you, Stuart. Thank you, Sam, for all of the great information we got on 1.3. Hopefully that gave those that aren't actively participating in the technical committee a better understanding of the technology that's laying behind all of the market use cases that came out of the initial Duckhorn use case definition that happened back in 2019.